Question 5. This question is about equilibrium. Then explain the effect, if any, of a decrease in overall pressure and equilibrium yield of SO3. So if you decrease the overall pressure, the equilibrium is gonna shift to the side with more moles of gas to oppose the decrease in overall pressure to increase the overall pressure. It's called Le Chatelier's principle. I forgot where it's something where if a substance is at equilibrium and a change has happened to it, position of equilibrium will change to oppose the conditions of changes. I'm not fully sure, but I know it's Le Chatelier's principle. Pretty sure on that. So if we decrease pressure, it's going to shift to side with more moles of gas, which is this side, because it's got 3 moles of gas. It's only got 2, and therefore the O on SO3 on SO3, yeah, the equilibrium yield of SO3 is going to decrease. Decreases. Because think about it, equilibrium is products over reactants. We're going to have more reactants compared to products. And then the text, why? What's going on? There we go, bring it here. Well, because if we decrease overall pressure, equilibrium shifts to the side with more moles of which is on the left hand side, hence equilibrium shifts to oppose decrease in pressure, hence increasing pressure. There's 3 marks you do need to talk about this. Decreases for 1 mark, because if we decrease overall pressure, equilibrium shifts to side with more moles, which is the left hand side, because that has more moles. That's got 3 moles compared to 2 moles on the right hand side, and therefore the equilibrium shift to opposite direction. It will shift, hence equilibrium shifts to oppose the decrease in overall pressure to increase pressure. 5.2, 5.3, and then 5.4. 5.2. A 0.46 mole of SO2 is mixed with that, and so you contain equilibrium reached. Mixture contains that much of SO3, having the partial pressure of SO2. Okay, so first things first, we're going to draw the table. So we've got M, C, E, and then we've also got MF, mole fraction, and then we can also add partial pressure as well. Partial pressure. So we've got SO2, we've got O2, and we've got SO3. We can end the table here. So how many moles of SO2 do we have? We've got 0.460 moles of SO2 is mixed with a 0.250 moles of O2 in a sealed container at a constant temperature. When equilibrium is reached, the mixture contains this many moles. So this is the equilibrium moles of SO3. So we've got 0.180. Before I carry on, M stands for moles, C stands for change in moles, E stands for equilibrium moles, EM, mole fraction, and partial pressure. So we're going to assume now that SO3 at the beginning was 0, so it increased by 0.180. Now if SO3 is increasing, the reactance, the equilibrium moles, must be decreasing. This has got a 2, this is a 1 to 2 molar ratio, so for O2 it's going to decrease by 0.180 divided by 2. And then for SO2 it's also got a 2, so it's going to decrease by 0.180. So let's do that. 0.460 minus 0.180, 0.28, 0.250 minus 0.180 over 2, 0.16, 0.16. Now to find the mole fraction is going to be 0.28 over the total moles. So it's going to be 0.28 all over 0.28 plus 0.16 plus 0.180, which is equal to 0.28 over, yeah, it's better if you just work out the total moles, which is 0.62. 0.62 moles, and I usually give a mark for this just to show the addition of the total moles. I can't really do that here. I'll just write total equals 0.62. So it's going to be 0.28 over 0.62, 0.16 over 0.62, 0.180 over 0.62. And now I can work at the partial pressures of each one by timesing it by 215. Because we want the partial pressure in kilopascals, so we're going to times it by kilopascals. However, we're not trying to find all of them. We're just trying to find the partial pressure of SO2 in this equilibrium mixture. So it's going to be 0.180 over 0.62. So the mole fraction, this total moles is in the moles of SO2. No, of SO2. Okay. See, just didn't read the question properly. Almost did it wrong. SO3. So SO2, so it's going to be 0.28 over 0.62 times by 215 total pressure. Mole fraction times by total pressure give us partial pressure. 97.1. 97.1 is equal to 97.1 kilopascals. And then 4.3 and then 4.4. So 4.3 says given expression for Kp for this reaction, calculate value of equilibrium constant for the reaction, give its unit. So expression for Kp is equal to SO3 squared, partial pressure of SO3 squared. So partial pressure SO3 squared, because there's 2 moles of it, all over partial pressure of O2 times by partial pressure of SO2 squared, because it's got 2 moles again, SO2 squared, just like SO3. Calculate the value of equilibrium constant. Well, Kp then is going to equal 1.85 times by 10 to the power of 2, 1.85 times by 10 to the power of 2 squared all over. Remember, it's not square brackets, it's curly brackets. Kc is square brackets, Kp is curly brackets. 1.02 times by 10 to the power of 2, 1.02 times by 10 to the power of 2 times by SO2, 1.67 times So we've got Kp as 1.20 times by 10 to the power minus 2, and the unit is kPa, kilopascal to the power minus 1. And in 5.4, what is the effect on value of Kp if the pressure of this equilibrium mixture is increased at a constant temperature? Final part, question 5, 1 marker. So if we increase, what is the effect on the value of Kp if the pressure of the equilibrium mixture is increased? Constant temperature remains the same. We're increasing the pressure of the equilibrium mixture. So which one is it going to be? Increases, stays the same, or decreases? Well, just like Kc was just only affected by temperature, Kp is only affected by temperature. Only affected by temperature, just like Kc. So the answer is stays the same, okay, no effect. And that is the end of question 5.